Welcome to the course on computer design, aided design of electrical machines. We will have a lecture 19 today on design of three-phase synchronous machine part 1. We will of course have a starting outline today with the introduction, then application, construction of different kind of synchronous machine with the generator, hydro and turbo, then synchronous motor, and then of course the electromechanical design of synchronous machine, followed by multiple choice questions and numerical questions, followed by reference. So coming to the introduction, the synchronous machines are AC machines having the field circuit excited by external DC source and the armature circuit with a three-phase balance winding excited by an AC source. In case it is working as a typically as a motor, like if it is a generator, then it generates the power from the stator side, which is normally armature winding on stator run. The armature circuit forms the stator of the synchronous machine and the field circuit constitutes the rotor in general in majority of machine, but inverted construction is also possible where we put the armature on the rotor and field circuit on the stator, which is used some of the applications typically like maybe a typically we call it like a brushless excitation system of large synchronous generators. I mean, this has been used in the inverted machine along with the main machine. However, for low power synchronous machine, the arrangement similar to DC machine can be used with the field on the stator side and the armature on the rotor side. So this is typically the first three-phase synchronous machine built by Frederick August Hesselwander in 1887. Then of course hydroelectric generator from Lapfan, now the HU Museum in Munich, which was evaluation of synchronous machine by Gerald Neffer in 1992 by ABB. So the background is the commercial birth of the alternator that called synchronous generator virtually can be dated back in 1891 and the first large scale demonstration of transmission of AC power was carried out, and this demonstration was so convincing about the feasibility of the transmitting AC power over long distance that the city of Frankfurt adopted it for the first power plant commission in 1894, and adoption of New York Niagara Falls power plant of the same technology and became operational in 1895. So this is typically the year-wise evaluation of the synchronous machine, especially the turbine driven generators and power rating, and you can see the power rating going to as high as typically of 1500 MVA starting from 300 kilowatt, like for low typically. I mean, this is normally for different kind of generator. Low speed is normally we call it the hydro generator and we call water wheel generator, and for large rating of course with the turbo generator which runs normally on high speed. So this was the beginning, and but after later on people developed even the machine with the 3600 RPM. So you can say synchronous machine, as you look into diagram, is normally used as synchronous generator. Normally the 90% conventional fossil fuel based generators like nuclear generator or thermal power stations, I mean they are all typically large turbo generator of round pole type, and of course a small low speed large rating water, we could call it normally hydro generator, we call it water wheel generator. They are normally the cell and pole construction. So these are, I mean, the most of the generation so far before couple of decade all works by synchronous generator only, because it has many properties as a generator. It can generate active and reactive power, and the voltage also can be regulated well, and frequency also well regulated by using the typically the governor system and voltage regulated by AVR, automatic voltage regulator. The other application here, as you see it, we have a synchronous compensator. This was also quite popular, and synchronous motor. So synchronous machine in general are classified as synchronous generators are the synchronous machine driven by steam or hydraulic turbine and generate electricity, and synchronous motor are the machine working on general power supply network at 50 Hz or 60 Hz and sometime at 25 Hz, and they are used in constant speed drive for compressor, blower and many other applications, including the induced draft and force fan in thermal power station. The synchronous compensators are, it's also called synchronous condenser, running the synchronous motor at leading power factor to supply the reactive power to the power system network, I mean in different segment of either transmission or distribution system, normally in transmission network for the reactive power compensation. So now coming to type of synchronous generator. In synchronous generator, DC excitation given to rotor winding which produces a magnetic field, and rotor is also driven by external prime mover producing a rotary magnetic field which induces three-phase voltages in the stator winding. And the classification of synchronous generator is based on type of prime mover and based on construction. So the first, coming to the detailed classification of this synchronous generator, first is a type of prime mover. So based on the type of prime mover used, synchronous generator are classified as hydro generator. These are generator driven by hydraulic turbine. They run at low speed, less than 1000 rpm, and Francis turbine, Kaplan turbine, and Pelter wheels are most commonly used hydraulic turbine to drive the synchronous generator. And another category is the turbo generator. The generators that are driven by steam turbine are called turbo generator. They run very high speed, above 1500 rpm for, you can call it normally 3000 rpm with 50 Hz and 3600 rpm corresponding to typically in case of North America with the 60 Hz. Then engine driven generator, normally we call it DG set, diesel engine driven generator or gas driven generator. So they are normally driven by various form internal combustion engine with the speed around 1500 rpm. You can just see the typical photograph of type synchronous generator. First is typically the hydro, second one, middle one is the typically you can look into driven, by let's say maybe steam turbines, and the last also you can clearly see the photograph related with the steam turbine. So now another is the classification, big classification on construction. The most widely used synchronous machine has a stator, armature, and rotating field system. These synchronous machines are classified into two types in accordance with the construction of rotor. So salient pole machine, normally these type of machine having a rotating poles with the concentric winding as shown in the figure, and this construction is adopted only for the slow speed machines, and it becomes very difficult to retain the salient poles against the large centrifugal. So they are used in hydro generator as well as wind power generation, which are driven by at low speed. Another non-salient pole, or it's also called cylindrical rotor machine. So here the field winding is not concentrated but distributed in several slots which are milled over the rotor surface as shown in the figure. So since the poles are not projecting, this type of construction can be used for turbo generator which have a high rotating speed up to 3000 rpm and above than that, like typically 3600 rpm, or for the gas turbine with the high operating at high speed like. So typical, you can see the construction here of salient pole kind of construction. Now it's a symbolic figure here as a projecting pole NS which are produced by the excitation. Normally these machines are not with the two pole, it decided by speed, like you might have 300 rpm. So the number of poles will be around 20 normally on the rotor, and on stator we have of course the armature winding, which normally in for large rating motor we have a typically double layer winding is shown here as a symbolic as a single layer winding. You can see salient pole machine cutway that you have a different parts. You have a typically even you have a damper bar in the slots of, you have a stator winding, and you have a poles with large number of poles as I already mentioned, used for low speed also. So we have a damper rings, we have a damper bar, we have a stator winding, we have a typically the field winding on rotor poles. So all the parts are typically shown here of the salient pole synchronous machine. Then the cylindrical rotor machine, as you can see here, stator winding is of course polyphase, three-phase winding. On the rotor you can say it's a of course cylindrical structure on the rotor, and we have a well distributed field winding to the periphery of one side of, normally two pole construction is there. So one third of the typically you can call it of portion, another one third, and typically the you can call it 1/6 portion is with the without the field winding. It gives a very good, because the air gap is uniform because of cylindrical construction operating at high speed. So usually we have a uniform air gap. So with the field winding distribution only we are able to make the field excitation, or you can say final flux in the air gap very close to the sinusoidal. Of course we should produce the sinusoidal voltage in the armature winding. So there are many methods by which really we try to make sinusoidal, and one of the methods that here is, because we cannot change the typical reluctance or payments to change the flux, so we use the distributed winding which really give a MF here similar to like a trapezoidal, which is closest to the sine wave, like to give the flux. So now coming to the applications, starting for small rating motor used for typically organ, then another synchronous motor with automated typewriting, then in microwave oven small motors, then a pair of ancient carbon dioxide air conditioning compressor by about antique 150 horsepower open frame synchronous motor. Then typically 120 volt synchronous motor used in micro oven for cooling and linear synchronous motor. Then saddle pole synchronous motor. Then synchronous hysteresis motor. Then you can see here the rotor of synchronous motor, typically with the cylindrical construction for large water pump. Then the synchronous generator used in micro hydro, typically to large hydro power applications. Then you can see the THECMO hydropower expansion project of very large rating. As you can see how they are assembling the machine typically at the site itself with the, as it is on the flag with different country there, and you can see how the size relative to the typically the person standing around like. Then this is another one, the rotor insertion of hydro generator, and here it is a 3 George dam in China, rating of 840 MVA with the 80 poles. So you can understand the speed will be quite low. You can see the size related to the human beings around like here. And the another hydro generator, here again of another photograph of the 840 MVA generator, and then in of course we have another generator of 350 MVA for hydro generator of 40 poles, runs at very low speed. Then synchronous generator used in diesel generation system plant. Then synchronous generator with the 2-pole generator customized for gas and steam turbine. Then synchronous generator of 4-pole generator customized to use in nuclear power plant. Then synchronous machine as a condenser. Of course, as a synchronous condenser, this has been fabricated about 260 MVAR, synchronous condenser like. So now coming to the typical construction of this synchronous machine, a 3-phase synchronous machine essentially consists of 2 parts, the stator and rotor. The fixed stator core carries the 3-phase balanced stator winding placed in the stator slot, that is armature, in the machine configuration, and the rotating field, also known as revolving field. Synchronous machine has the field winding on the rotating member, the rotor, and the armature wound on the stationary member on the stator, as you can just see typical diagram like. So schematic cross section area of 7-pole synchronous machine, the 7-pole as we have shown, and 3-phase voltage obtained at the terminal of armature, which are supposed to be closer to sine wave, and the frequency are decided in hertz is number of poles P into RPM divided by 120. So now if you look into the parts of synchronous machine, in synchronous machine parts start from stator, then the winding in the stator, rotor winding, and then shaft and bearing and frame. You can clearly see 2 kind of the machine as a construction of synchronous motor. The left side is 7-pole construction, as you can see projecting poles with the slip rings that you have to give field excitation, and your armature winding on the stator, which you excite by 3-phase supply. On the right side you have cylindrical pole machines, normally with less number of poles, and here for simplicity is shown for the same number of poles, but it's a distributed winding so that it give you sinusoidal flux in the air gap. And then we have armature winding on the stator. These are the typical nameplate of these synchronous motor, made by General Electric and Hitachi for generator, and synchronous motor by General Electric, like to the rating of typically 21,000 horsepower synchronous motor and typically 387 megawatt synchronous generator. Then another steam turbine generator, nameplate, you can clearly see here what are the specifications given, starting even type of cooling, then the rating, power kV rating 120, typically your you can say 12.8 MVA, and on the right side typically another generator rating of 2351.2 kV of 6.6 kilowatt 1000 RPM synchronous generator like. Now coming to construction aspect of synchronous machine, for the construction of cylindrical machine and cylindrical machine, the following parameters are of importance: the peripheral speed and centrifugal force, critical speed and runaway speed. So the peripheral speed and centrifugal force, here peripheral speed of the machine is given by V equal to pi d ns in meter per second, where d is the diameter of the rotor in meter, ns is the speed of the rotor in revolution per second, and this comes as a peripheral speed. So it has a different limitations of peripheral speed. So volume d square L of the machine has to be increased if the power output has to be increased. So however it has to be noted that d cannot be increased to any extent. So there is a restriction imposed on the diameter d. So for pole to pole 50 hertz machine with ns equal to 50 rps, d equal to 1.2 meter, then VA 180 8 meter per second. This is the maximum possible peripheral speed, and the corresponding centrifugal force is maximum which a rotating mass can withstand. Now coming to typically critical speed, the static and dynamic balance of a large rotor must clearly be secured to avoid any dangerous condition. And for example, the rotor is a structure with its mass running in two bearing. If the mass center of the rotor of mass m is displaced by eta from the center of rotation, then the centrifugal force exerted on mass will be m omega square e, where omega is the angular velocity, and this will cause deflection delta in the shaft, increasing the centrifugal force to m omega square sigma plus eta, and this force opposite to the counter force k is sigma k delta in the shaft. For equilibrium, these two forces must be equal, giving delta equal to mv square eta divided by k minus m omega square. So critical speed here, your delta equal to m omega square eta divided by m minus k minus m omega square. So at some angular velocity, say omega c, called critical speed, the denominator becomes 0 and the deflection becomes infinite, which is dangerous for the machine. So designer must aim to make the machine to operate at a speed away from critical speed as far as possible. Now coming to runaway speed, when a full load is suddenly thrown off, the prime mover tries to raise it as it will be receiving the full supply of water or diesel or steam from their respective prime mover, the speed called runaway speed, and water will generate. The speed governors are not quick acting like turbo generator. The runaway speed may be as high as 2.8 times of the rated speed, causing great mechanical stress, and machine must be designed to bear such great forces. And the maximum peripheral speed for which silent pole is designed is generally 140 meter per second, while turbo alternators are designed for a maximum peripheral speed of 180 meter per second. So, well, now coming to construction of hydro generator, there are silent pole machines running at low speed. The construction mainly based on the type of turbine and water wheel available. So, for given frequency, a large number of poles are demanded at low speed. So, this type of machine will have a large diameter. So, with diameter as large 15 meter, it is just not possible to transport the machine as a single unit. Therefore, it is designed to be transported to site in section, and the machine will be designed to withstand the centrifugal stress produced by a convention. Now, the overall inertia of the set is mostly determined by the turbine governing and the transient stability of the associated power network, with the generator being responsible supplying most of it. So, typically machines are designed to rotate safely at speeds about twice the normal operating speed. It is rare for the overspeed to be close to the first critical speed. So, horizontal and vertical shaft designs are used, with the horizontal shaft used for the impulse turbine drive and the vertical shaft employed for large reaction and Kalpan turbine. So, well, this is typically, you can see the different parts of the hydro generator, with the starting from stator, then silent pole rotor, frame, windings, and of course 3-phase power supply connected to stator winding, then the rotor and DC supply. So, it's a, you can call parts of synchronous motor silent pole. So, here you can see how the typically the stator of synchronous machine is shown here with the winding in the stator like. So, now the bearing of horizontal shaft machine must include a thrust bearing to resist the axial component of the force produced by the turbine. So, within low speed vertical machines, the hydraulic force may surpass the weight of the rotating mass. Additionally, there are several potential variations in the mechanical configuration of the unit, and here you can just see the different parts of hydro generator and turbine control scheme like. So, now you can come to the stator of this as a part of construction of hydro generator. The stator core is made of lamination of low silicon steel, usually CRGO, cold rolled granulated steel, and the core is supported by dovetail key bars to the outer cylinder frame called yoke. So, the stator of large machines is manufactured in 3, 4 or 6 sections, occasionally fully wound except for coil joints to elevate transportation difficulty, and utilizing guaranteed magnetic sheet steel is feasible. However, the benefit is not significant. I mean, this is application of guaranteed steel, as you can see part of your stator core, and just see the stator stack core cross section area, I mean of different part that is shown in the typically photograph as well as on the side of this is how looks like a stator stacked core. Then the top view of single lamination steel, how the single part of its stator lamination look like. Then you can say welded stator housing of a synchronous hydro generator, as you can see compared to the, I mean like a size of a person standing there, then how big is the size of the stator. Then assembling of stating of stator frame to form the core. Then the passing of lamination stator iron core with the hydraulic cylinder. Then the three-phase windings are placed inside the slots of laminated stator, and multi-turn coils are generally used, as you can see the coils in the part of stator segment. Then you can see how look like a stator winding. Typically the big generator only use one turn per coil. Coil is split into two halves, 2 bar. Here visible insulating 1 bar for 2-pole turbine generator with the glass fiber band with mica layer for the high voltage insulation. So insulation of high voltage stator winding with typically insulation robot. So typically the 2-layer diamond coil form is normal with the single bar or multi-turn coil. Bar winding have probable or similar transposition arrangement, and the insulation is generally of class B mica with nomic epoxy or polyester bond varnish, as you can see in the photograph. So you can just see how it looks like a stator winding with the winding overhang, coil side inserted normally in the slot, and then the coil terminal. So high voltage form the wound stator coil of the several turns, and see for 2-layer winding. Then here you have a typical stator winding, as you can see different parts of this with the ventilating duct, 2 slot, massive iron clamping fingers, pressing plates, and typically the layers, first layer, second layer, and then the winding overhang which is coming outside like. Then typically the high voltage stator winding of synchronous hydro generator, pressing of winding bar in the slots. Now coming to construction of the rotor for this hydro generator, the salient poles are carried on the rotor body. The type of rotor construction largely depends on the peripheral speed. The rotor poles that are laminated are bolted to the rotor body for low peripheral speed up to 25 meter per second, and for higher peripheral speed dovetail T-type rotor is used. So you can say both type of T head type rotor and dovetail rotor like. And this construction typically of hydro generator rotor, as you can see here. And then the typically here you can see how the rotor poles look like: dovetail fixation, cooling fins in case with the copper width, and damping ring, damper bar virtually rings, and damper retaining bolts, the rotor back iron, rotor spider, and general generator shaft. I mean, so completed big hydro salient pole generator, synchronous rotor for high centrifugal force at a over speed of 414 poles. Then you have a rotor with the pole shoe built as limited iron stack to suppress the eddy currents which are induced by slot triple magnetic air gap filled due to the stator slot opening, and here slots for damper bar. Manufacturing of poles for high pole count and low speed ring generator. And here it is a rotor rim adjustment after the stacking the lamination, as you see in the photograph, and rotor cut wave and assembly with the different parts like. Then you can have a fixation of rotor poles with high centrifugal forces. Along with that, you can recognize the damper ring segment, pole press plate, pole joint plate, 3-fold hammer head fixation. Then you can see how look like a linear guide rail and upper guide rail fastener, assembly of the rotor pole supporting parts, and then segment of sleeve bearing for vertical load, and detailed view of bearing segment for the vertical load with the bearing. Now coming to typically the rotor windings, as you can see in the photograph, the rotor coils are formed from rectangular section strip of copper or aluminum wound on a edge with interturn insulation that is cured and consolidated under a pressure greater than the centrifugal force exerted on the coil during the overage feed. The coils of machines with the auxiliary long poles are fabricated from the punch straight length of copper as shown in part of a figure, and certain turns can be made with wider step to the produce external cooling fin, and this method also facilitates the construction of centered field winding as shown in the part of B figure, which better withstand centrifugal force. You can see how it look like a rotor winding typically of this non-insulated that copper winding provides a good heat transfer to be cooled air at the front side and internal insulation and cooling fins by induced copper and typically the manufacturing of field winding for silent pole machine. And you can see 3-fold hammer head fixation and cooling fins by increased copper width and dampering segment. Like now coming to typically again part of rotor winding, we have a damper winding, which really is a mandatory either in motor and generator both. So these are applied to control oscillations hunting in the machine. They are copper bars placed through the slots in the pole shoe with the end connection attached to the pole and plates, and they are also used to provide starting torque in the synchronous motor. Like so, in generator they use to avoid the hunting as well as in motor, but in the motor they also provide the starting torque. Like so, damper winding provided in synchronous machine consists of low resistance copper, aluminum or brass bars housed in slots in the pole faces of the silent pole machine, and projecting ends of the bars are also connected to short circuiting rings on both sides, similar to the squirrel cage winding in induction motor. They are classified two types: non-concentrated incomplete damper winding and concentrated complete damper winding. So now coming to typically non-connected damper windings has dampers in each pole face and are independent from each adjacent pole, as you can see typically on the left side. And in connected damper winding, dampers are continuous between the poles, and modern synchronous machines are provided with a connected damper winding. Now coming to cooling of hydro generators, the most hydro generators are air cooled for cost, simplicity and reliability reason, and fans placed on the rotor shaft are also used to circulate the air either in the axial or radial direction, and the heat most commonly removed by air to water heat exchanger placed on the stator frame or close to the stator frame. It is feasible to have the air circulating in the closed loop to minimize the risk of dirt exposed to the winding and air duct. So now coming to construction of turbo generators, a 50Hz turbo generator is essentially a 2-pole machine running at 3000 rpm. The diameter of the rotor is limited to 1.2 meter because of the regions of stated earlier of transportation and as a 1 unit, and this machine has a high efficiency at high speed. So to increase the rating axial length, electrical loading and magnetic loading of these machines are exceptionally high. So this increases the temperature of the machine. So sophisticated cooling mechanism like hydrogen cooling or direct water cooling are adopted in these typically turbo generators. Like you can see here how stator look like of turbo generator. The stator core is built with the segment laminations, and the slots, ventilating hole and dovetail keyholes are punched together, and you can see how the typically your stator is stacking of the large rating turbo generators. Like so, 3-phase double layer as far as stator winding, 3-phase double layer and short pitch coils are used and are placed in the slots of the stator. We use the short pitch, which reduces the overhang as well as eliminates some of the harmonics in the induced EMF to make the induced EMF sinusoidal. Now coming to the rotor, rotor is a cylindrical structure made of solid forgings of alloy steel, and the surface is milled to form the slots, and normally about 2/3 of surface is slotted and rest is unslotted, and concentric multi-turn coils are used. You can see how it is partly slotted structure with the part of winding, which gives the trapezoidal MMF and the really eliminate the harmonics in the flux in the air gap, because air gap is uniform here. Now this windings wound on the rotor, you can see how it look like in the photographs on the left side as well as on the typically on right side, and setting of rotor with iron seats, the rotor slots with field coils and damper cage and concentric field coil. So you can just see how the different parts stator housing, stator 3-phase windings. Stator winding is normally star connected to provide the neutral. I mean maybe like UVW with the N as a star point, and of course short circuited for protection during the assembly, and typically the field winding, damper cage and rotor spider. So now about the cooling of this turbo generator. So turbo generators conductor cooling is normally either by conventional or direct gas like hydrogen cooling or direct water cooling in 3 cases of ABC. So now you can see how the typically the construction cross section of direct water cooled Robel stator bar, where the main insulation is made with the astrophyletic mica splitting insulation, and this is typical of large turbine generator stator made before 1960. And now basic configuration of AC superconducting synchronous machine use liquid gaseous helium cooling. So now typically turbo generators have forced ventilation and total enclosure to deal with the large losses and high rating per unit volume. And direct gas cooling, large stator cores for turbo generators are provided with both axial and radial ducts and high thermal conductivity, reduced temperature gradient, high specific heat and non-supporting construction are the benefits of use of hydrogen in place of air as a coolant. And for the direct water cooling, the turbo generator of highest rating so far contemplated are likely to have a hydrogen cooled stator core and direct water cooled stator and rotor winding. So thermal capacity of water is 750 times that of hydrogen at 500 kilonewton per meter square, but there are limits to on the peripheral speed of water flow in channel, that is 2.5 meter per second, to avoid the erosion or cavitation. And nevertheless, the conductor water duct area may be small, allowing more space for power. Now coming to the synchronous motor, the synchronous motor have a similar construction as that of synchronous generator with rotor construction mostly with the silent pole. And these motors are non-self-starter, so they are started with the help of damper winding. Now coming to material and behavior. So coming to core material, it is, if it is feasible to choose a favorable magnetizing direction, the use of cold rolled oriented steel has a possibility in machine. If two-pole generator, turbo generator, the cold flux direction is mainly circumferential in the parts external to the slotted as shown in A. In large hydro generator, it is the teeth rather than the core that may benefit, and the arrangement B may give some reduction in both excitation and core loss. Typical application of guaranteed steel. And now pole material. The laminated poles are used on all medium and low speed construction, and they comprise the thin steel plates clamped between heavy end plates and the secured by stud and or rivets. In case of low and medium speed, the body is fabricated from a cast steel spider mounted on shaft. For a high speed, the rotor body is normally machined for single ingot forging, and for strength up to 800 meganewton meter square, the nickel chromium vanadium molybdenum steel is used. Now coming to typically conducting and insulating material, turbo generators. For turbo generator, excitation current may reach 2.5 kiloampere at 1 kV for a 750 megawatt generator rotor. So for lower rating with conventional cooling, the winding comprise continuous coil of silver bearing copper strap, and with tapered slot and direct cooling, the coil sides are constructed separately and joined at the end of after location in the slots, and the end windings not being retained by the slot wedges must be contained with the end balls. To reduce the rotor flux leakage, it is the European practice to use these non-magnetic austenitic steel, that is 18% manganese, 3% chromium and 0.5% carbon, of ultimate strength reaching 1150 meganewton per meter square. Now in turbo generator, the typically conducting and insulating material, the conductors are insulated by mica paper or asbestos or glass fiber tape with polyester or epoxy bonding to give a mechanical strength and permeate. And the end windings must have very secured brace against movement under the impact of short circuited electromagnetic forces. And hardwood blocks with the grass fiber cord or tape may be used with metallic but non-magnetic bracket as anchorage. And typically for hydrogenerator, the field coils are formed from the rectangular section copper or aluminum strap on edge with the internal insulation cured and consolidated under the pressure exceeding that due to centrifugal force on the coil at over speed. The coils of machine with the axially long poles are fabricated from punch straight length of copper, and stator winding is normally in the form of a two-layer diamond coil with class B insulation. So coming to now electromagnetic design of synchronous machine. So for electromagnetic design in silent pole synchronous machine, the air gap is non-uniform. In addition, the windings are placed on the rotor in an unsymmetrical manner. Hence, the equivalent circuit view from each phase depends on the instantaneous position of the rotor. So analysis of synchronous machine can be done by performing the equivalent circuit representation of the stator into two circuit components. One of the circuits portray the behavior of fluxes and current in the field axis, that is called direct axis. The other circuit represent the flux and current in the interpole axis, that is called quadrature axis, and these two circuits are fixed relative to the rotor axis and are set to rotate with the rotor, or the stator frame rotates with the stator. The synchro machines are nearly designed such that the magnetic circuit, particularly rotor pole, is highly saturated, and superposition scheme based on the computing the flux produced by the field and then by stator MF independently and adding the result is not applicable here. To avoid the complications of rotor resiliency of the synchro machine, and in ideal pole shape is in which the gap is uniform and the negative flux is in the interpolar space is considered. As you can see, the diagram have field coil with the current is there coming from the rotor side, simplified geometry coil with the silent pole synchro machine. So these are of course the notation the what we'll be using here. Phi for magnetic flux in Weber, A is the area of magnetic path in meter square, and L is the length of magnetic path in meter. B is the flux density in Tesla or Weber per meter square. H is the small at magnetizing force or ampere per meter, and capital AD is total MF in ampere. Mu equal to mu r into mu 0 absolute permeability of magnet material in Henry per meter. Mu 0 is the permeability of free space 4.10 power minus 7 Henry per meter, and mu r is the relative permeability. S or R is the reluctance in a ampere per Weber, and rho or P is the permeance in Weber per, and Im is magnetizing current per phase, anti-phase is the turns per phase. So coming to calculation of magnetizing current, the total MF must be provided by exciting winding, the sum of MF of several series parts of the magnetic circuit. The value of exciting or magnetic current depends upon the total MF required, the number of turns in the exciting winding, and upon the way in which the winding is distributed. So typically for coming sinusoidal flux distribution, if the flux is steady and its sinusoidal distribution in space, the value of magnetizing current is Im equal to MF for peak flux density Pm divided by winding turns, so Atm by T, and three-phase winding uniformly distributed with 60-degree phase spread and excited with balanced sine wave current give the amplitude of fundamental magnetizing Atm equal to 2.7 IMTPH Kw1P, and non-sinusoidal fluctuation due to saturation MMF wave becomes the flat topped instead of sinusoidal distribution. So B0 becomes Bm1 sin theta plus Bm3 sin 3 theta, Bm5 sin 5 theta. So B0 flux density at angle theta from neutral axis, and Bm1, Bm3 and Bm5 are the fundamental and harmonic component of flux density B. Well, calculation of direct and quadrature axis magnetizing inductance, assuming the three-phase balanced sinusoidal voltage input to the stator resulting in a uniformly rotating MF stator MF wave, though neglecting higher harmonic, the stator MF rotates asynchronously in air gap. So that is Fs equal to Fs1 cos p theta by 2 minus omega e t, and where Fs1 is the amplitude of fundamental component of stator MF obtained from S1 equal to 3 by 2 4 by pi K1 T1 Nt by P Is upon Cs, or equal to 3 by 2 4 by pi K1 S upon P into Is, where Is is the amplitude of current in each of the three-phase stator phase, and S is the series connected turns, and the subscript S for the added to here number of stator parallel circuit C for the eventually clarity when the rotor field circuits are considered. So this is typically air gap flux density with D axis armature current and the zero field. I mean, as to just show typical example of. So coming to now in terms of DQ component, the peak stator MF for P poles for balance conditions can be given FDS1 equal to 3 by 2 4 by pi K1 Nt by P ISCS into cos theta, or equal to 3 by 2 4 upon pi K1 SNS P into ID for direct axis, and for quadrature Fx Q1 QS1 that is 3 by 2 4 by pi K1 Nt upon P Is upon Cs sin eta 3 by 2 4 by pi K1 S NS upon P into IQ in quadrature axis. So ID IQ are the expressed in sequence rotor frame. Angle eta is the spatial location of the peak value of stator MF relative to direct axis in term as MF angle, and each of the MF components produce the corresponding flux density such that air gap flux density Bg theta is considered being comprised of two components, namely Bg theta and BQ theta. So to calculate the direct axis self-inductance, it is assumed that the machine is excited by direct axis component of stator MF and leakage component is neglected for the moment. Assuming a uniform air gap under the pole and essentially infinite in the interpole space, assume that the flux goes straight across the gap and bringing flux in the interpolar space is neglected. The magnetizing flux linkage of one pole is obtained by integrating the gap flux density over the one pole in the direct axis. Stator flux linkage per so lambda mdp equal to le dis by 2 and integration minus pi by b2 plus by 2 and ds as a function of theta, bgd as a function of into d theta, where dis is the stator inner diameter and L is the axis length of the machine. So neglecting the spectral harmonic, the winding function corresponding to IDS is equal to NDS equal to 4 by pi k1 and nt upon p sin p theta by 2, and since the gap is assumed as uniform over the polar at 2 alpha pi upon p, the gap flux density BGD produces FDS is sinusoidal over the region with amplitude BGD and 0 elsewhere. So direct axis linkage equation becomes lambda mdp equal to 4 upon pi k1 nt upon p and integration minus alpha pi upon p to alpha pi upon p bgd1 cos square p theta by 2 into le into dis upon 2 into d theta, that becomes equal to 2 upon pi k1 to nt upon p bgd1 tp le in bracket alpha pi plus sin alpha pi by pi, where the tau p equal to pi dis upon p and bgd1 is the peak flux density of air gap, peak value of the air gap flux density fundamental component produced by d axis MF in case of smooth air gap where alpha equal to 1. The total flux linkages produced by d axis are equal to the number of poles connected in series. So lambda is d p upon cs into lambda ft, that is 2 upon pi k1 ns bgd1 tp into le into kd, where ns equal to nt upon cs, where kd is defined as kd equal to alpha pi plus sin alpha pi upon pi. So direct axis magnetizing inductance is equal to the flux linkage produced by the stator current divided by the d axis component of stator current. Therefore, the equation define MF and flux linkage lmd equal to 12 upon pi square k1 square ns square by p and pgd1 divided by fds1 into tau p to le into kd. So peak flux density of d axis, that is fds, is related to peak value of d axis MF related to peak flux density in the air gap given by fds1 equal to bgd1 by mu 0 into GE, where GE is the effective gap for the direct axis of machine including the effect of both fringing and saturation. Finally, the d axis magnetizing inductance becomes lmd equal to 12 upon pi square into k1 square and s square by p mu 0 tau p le upon g into kd. So the similar process is done for quadrature magnetizing inductance. So it is necessary to align the quadrature axis with the synchronously rotating stator MF or assume the excitation only by q axis MF. The equation describing the total air gap flux linkage for all four in quadrature axis is lambda q mq equal to le dis upon 2 p minus pi upon p to pi upon p and qs as a function of theta, bgd as a function of theta into d theta, where the winding function and qs theta is defined as nqs theta equal to pi upon p k1 nt upon p cos p theta by 2. So this equation becomes lambda mq equal to 2 upon pi k1 ns bgq1 tau p le into kq, where kq is given by kq equal to l alpha pi minus sin alpha pi divided by pi, and using the equation for the quadrature axis magnetizing given lmq equal to 12 upon pi square k1 square ns square by p mu 0 tau p le upon g into kq. So the function kd and kq are plotted as a function of per unit pole arc alpha in figure. You can see kd how it is changing with the alpha. So the value of kd kq as a function of per unit pole arc alpha. And this is the air gap flux density with the field excited and 0 armature current. Then the coming to now field magnetizing inductance. So let the gap flux density bgd theta is a constant equal to bgf pk over the entire pole when they express in terms of fundamental component of square wave. The useful magnetizing air gap portion of the field flux linkage per pole is given by lambda mf p1 equal to 4 upon pi n tf upon p le dis 1 by 2 and integration from minus alpha pi b to alpha pi p bgf p cos p theta by 2 into d theta. So ntf is the total number of field turns, and this equation reduces to lambda mf p1 equal to 8 upon pi square ntf by p into le to bgf p kf and t. T top P. For all poles in series, lambda MF1 equal to P upon CF into lambda MPP1 and equal to 8 upon pi square NF LE BGF peak KF top I, where CF is the number of parallel field circuit, NF equal to NTF upon CF and KF equal to sin alpha pi upon 2. And since MF drop over the pole circuit is alpha P equal to NF IF upon CF divided by P upon CF. So KF is defined as the product of KFA times KFB. The magnetizing portion of the field winding inductance correspond to CF parallel circuit is LMF equal to 8 upon pi square NF square LE tau E BGFP upon FP FP KFA and KFB equal to 8 upon pi square NF square upon P LE top of E mu 0 KFA KFB. And this is the curve for calculating KF obtained from my finite element plot KF equal to KFA and KFB. I mean both the functions are plotted with respect to the your typically polar arc upon pole pitch as well as minimum gap upon pole pitch. Now coming to calculation of rotor pole flux leakage permeance. So when the leakage flux is associated with winding carrying steady state AC, reactive voltage is produced, though magnetic reactance offered by leakage flux is predominantly due to air gap under the normal condition, and so leakage reactance is directly proportional to the current, giving a constant inductance. Therefore, the reactive voltage may be regarded as due to the voltage drop in the constant leakage flux reactance. So, well, it is impossible to confine all the flux to the magnetic circuit. The alternating leakage flux induces voltage in the winding to which it is linked, also known as leakage flux reactance, leakage reactance voltage, and this reactance play an important role in AC machine. The estimation of leakage flux is difficult due to complex geometrical path of leakage path, and typically you can see how the typically stator body leakage flux, underline pole tip leakage flux, pole tip leakage flux, and phi 4 psi 4 and leakage flux and phi land. So all 5 leakage flux are shown here in the different parts of for this pole body leakage. Now coming to specific permeance, the leakage flux can be assumed to consist of flux tubes of the length y and constant width delta x along with the effective depth of L of the field. So tube permeance is delta rho equal to mu 0 area of the tube divided by length of the tube, that is mu 0 L delta x upon y, and permeance of the whole flux, that is delta equal to mu 0 integration L dx upon y, that is L equal to mu 0 integration dx upon y, and stress permeance lambda equal to your psi upon L, that is mu 0 integration dx upon y, that is specific permeance is permeance per unit length. And you can see the how the leakage flux is really in different parts of the this portion of the machine. Now coming to leakage reactance, when leakage flux is associated with the winding carrying steady state reactance voltage is produced, the magnetic reactance offered the leakage from permanently due to air path under normal conditions. So leakage reactance is directly proportional to the current, giving a constant inductance, and therefore the reactance voltage may be regarded as due to the voltage drop in a constant leakage reactance. So now leakage reactance, the coil with T turns with current IZ, effective permeance of flux path. So inductance defined as a flux linkage per unit of the current. So inductance equal to flux linkages of the winding divided by current. So T phi upon IZ, and phi equal to MF in permeance, that T into IZ into rho, and inductance is T square IZ into rho by IZ, that is T square rho. So now coming to multiple choice question related to the material what we covered today. On the basis of type of primary synchronous machines are classified in all 3 parts: turbo generator, hydrogen, hydrogen, and starting of the synchronous motor may fail due to single phasing, low voltage, or overhead. So this is true for all. The determination of the full torque in the synchronous motor running condition may be open or this to any, and is typically used in stator core for turbo generator, both cold rolled and there is a segmenter. And sound due to hunting is produced in synchronous motor when both load fluctuations or supply voltage vary, and the material used in rotor of a turbo generator is due to forged steel. The type closed circuit air type of cooling used in cooling of hydro generator. In turbo generator, the rotor winding tool range is 1.2 in turbo generator, and turbo generators have a small large diameter of core, a small diameter and large core length. Alternators are driven by hydraulic turbine are designed to operate at speed of 150 to 600 rpm. The rating of alternator are usually specified in kV or MVA. In case of higher rating turbo generator, maximum rotor diameter can be order of 1.2 meter. The steam turbine driven generator are highest rotating speed. Steam turbine driven alternator usually least sufficient. The damper winding in synchronous machine used for reducing oscillation and hunting, and use of silent pole on a high speed generator will cause the rotor pole both the first and second. Now coming to subjective questions. Why are the poles who are chamfered for silent pole machine? Tampering is done in the pole shoe for silent pole synchro machine to provide the uniform distribution of flux of pole region. What are the type of rotor used in engine driven alternator? Silent pole construction is adopted for the rotor. These alternator as the design speed is generally lower. Mention the reason for non-use of silent pole alternator for high speed. Following are the reason for affecting the silent pole. Mechanical stress on rotating part, winding loss is high, noise is high, and in the case of high rating alternator, what is the relative position? The high rating motor, the armature is stationary where the field winding is rotating. They give the need for damper winding in synchronous machine. Damper winding provided in synchronous machine has the following reason: reduces the overvoltage or abnormal condition, help in preventing oscillation or load fluctuations or steam system disturbance, and damp out hunting by producing the proper additional torque, help in starting as the cage winding as an induction motor. What type of hydraulic turbine suitable for as the primer for hydrogen having water wheel head above 400? Pelton wheel turbine is suitable for primer of hydrogenator order above. What is the limitations factor for the diameter of synchronous machine? Mention a typical value of cylindrical and cylindrical. The limiting factor for diameter for synchronous machine is the peripheral rigidity. Typical value of peripheral rigidity are 175 meter for cylindrical auto machine, 80 meter per second for cylindrical machine. Discuss about the factors that are considered in the design of field system model. The factors that are to be considered in the design of field alternate number of poles, voltage across each field coil, ampere turns per pole, copper loss in the field coil, and dissipating surface area of the field coil. Mention the advantage of fractional slot winding used in the synchronous machine. In low speed machines with large number of poles, the fractional slot winding uses the tooth harmonics. A range of machines with different can be designed with the single limitation. It reduces the harmonics in MF and leakage reactance of the winding. It allows to use only short circuit winding. Therefore, the length of mean turn of the which results in shorter and connection of save the winding in copper. How does the damper winding act? What is the alternator running at a speed slightly below the under the above condition? Damper winding produces a torque in the direction of rotation, which accelerates the rotor and running to attain the synchronous speed. Mention the factors which are considered in selecting the number of poles in order. The choice of number of poles depends on the speed of primer and frequently used. The Y turbo generators are designed for a smaller diameter and large length, where the water wheel generator have a large diameter and a small length. The turbo generator operated at high speed, hence to limit the peripheral centrifugal force with the diameter, but in obtaining the required output, an appropriate value have to be maintained. It leads to increase the length. The water wheel generators are operated low speed, hence the large number of poles which cause the reduction in speed. In addition to large number of poles require large diameter, which leads to reduction in length for obtaining required output in approach. Now coming to numerical problem. Numerical problem: a typical synchronous machine with the mean flux density is B equal to 0.5 Tesla. The slots are spaced 40 mm per part for each contain conductor of 35 mm into 12 mm. Current density is delta 3.3 mega ampere per meter square, that is 3.3 ampere per meter square. Find the tangential force per unit length of gap periphery per axial length of the machine. The specific electric loading A equal to area of conductor current density into slot opening. Putting the value, it comes 35,000 ampere per meter. The specific force B into A, that comes, putting a value, your 17,500 Newton per meter square. Coming to numerical problem 2, for two-pole machine, find the magnetic pull per pole when its axis is displaced equal to 0.00 meter or 1 millimeter. The machine have a D equal to 0.5 meter, L equal to 0.2 meter, L equal to 0.005 meter, that is 5 millimeter. The stator and rotor peak current sheet density are A1 equal to 1200 ampere per meter and A2 equal to 9600 meter, and the torque angle is equal to pi by 3 radian. So MF per pole is F1 equal to half A1D, that is 3200 ampere turns, and F2D AD, that's a 2400 ampere turns. So result MF per pole is obtained F0 square F1 square plus F2 square plus 2 F1 F2 cos delta, that is F0 445080, and the peak value of flux density processes in the air gap Bm equal to F0 mu0 upon Lg, that is 1.11 Tesla, and magnetic pull per pole is calculated dl b square Bm square by 3 mu0, that is 33 kilonewton. Now coming to numerical 3, 3.75 MVA, 10 kilowatt, 3 phase 50 Hz, 10 pole low speed hydrogenator has a 144 slot containing 2 layer diamond winding with 5 conductor per coil side in each slot. The coil is 12 slot per piece. The flux per pole is 0.116 Weber. Calculate the chording angle. So slot angle is given by lambda gamma equal to 2 pi s 2 pi p upon s, that is 10 pi upon 1 body, that comes 0.218 radian or 12.5 angle degree. The fractional value of the slot per pole per phase G dash equal to S upon 2 MP, that is 4 into 4 by 4, 4 upon 5. So there is a sequential, consequently 24 pole slots per phase, that is 72 slots in all, in each pole 5 slot, and total MF flux per pole phi 1 equal to 0.116 Weber. The third harmonic flux is ignored, it does not affect the line. So coil span is given by slot pitches divided by number of phases, number of slot pole, putting value it comes pi by 6 pole pitch or 150 degree. Chording is done by eta equal to 30 degree. The chording factor is given K Cn equal to cos half n eta, and that comes cos half n 30 degree, and that's the distribution factor is Kdn equal sin half of n 60 divided by 24 half 2 eta and 2 1 by 2 degree. The EMF is calculated EMF equal to 4.4 Kd and 5 F1T, that becomes here 5750 volt. Now these are the references which we followed for preparing this material. You can refer them. Thank you.